My name is Chavez. I'm a research student at New Mexico State University, and today I'm going to present a solution that focuses on solving instabilities found on neuromorphic machine learning implementations. So before we jump into our proposed algorithm for stabilization of synaptic weights, we need to address some concepts to have a clear picture of the problem we're dealing with. And this one involves Hebbian learning. So in Hebbian learning, we know that if two neurons on either side of the synapse are activated simultaneously, then the strength of those is going to be effectively increased. In other words, neurons that fire together wire together. And this activity causes the synaptic strength between these neurons to increase, in this case, the weights. And this phenomenon is called Hebbian plasticity. And however, over time, Hebbian plasticity could cause some stability problems. And since Hebbian, this is a positive feedback process, effective synapses are going to be either strengthened or ineffective ones are going to be weakened. So these behavior destabilizes the pre and the post synaptic firing rates, reducing them either to zero or increasing them excessively. And there have been numerous mechanisms for synaptic regulation or either homeostatic plasticity. One of them is called slow wave sleep. Other ones involve synaptic scaling, which consists of globally adjusting all the synapses based on the level of activity or synaptic redistribution. In our case, in this work, we propose a neuromorphic algorithm that directly normalizes a synaptic connectivity with a neural circuit using a SymFire-gated SymFire change-based information control network, which works in concert with Hebbian learning. And this normalization circuit, we implemented this network with LCA. And LCA stands for Locally Competitive Algorithm, which is a dynamically sparse code solver that uses only local computations to learn dictionaries of convolutional kernels in an unsupervised manner. And as we see on the right, we have the LCA architecture where each of the dictionary elements are denoted by phi. And in here, we see the boxes represent neuronal populations, and the information interchange between them is denoted by the arrows that we have between them. Also, inside the boxes, the equations in them, they represent the pre and the post synaptic activities of the neurons. And on the left, we have the normalization figure, and we see here how our normalization network can be implemented as a component of LCA. And we know that LCA works with the reduction of the cost function, and our normalization algorithm works as a add-in component to the LCA, which is this one that we have on denoted by red. And now focusing on the cost function on that normalization component. And this one works by the multiplication of dictionary elements by its transpose and the subtraction of a vector of 1. This computation will cause phi to be minimized between its value and a vector of unique length. Consequently, if the vector, if the connectivity matrix has a length of 1, it will not have any effect. Otherwise, if the connectivity matrix is not the value of 1, it will have an effect of the synaptic updates, and it will try to reduce the values to length 1. And to minimize this cost function, we use gradient descent, where the update is denoted by the new and old subscripts, which will help converge the synaptic connectivity values of phi to unique length asymptotically. And in order to do this on the neural network, we use a process of gating, which from a backpropagation algorithm, which we also developed previously. In here, the information flows through the network normally. However, if this information is being controlled by SimFire gated neurons, which are represented with the yellow box. And one of the things that we have to highlight is that we're not going to have any flow of information through the network if we don't have any activity on the SimFire neurons. So then the SimFire neurons potentiate the network neurons, allowing them to reach a firing threshold. And going back a little bit more in detail about the architecture of the normalization circuit. On the left, we show our normalization network architecture. In here, we have 3 neuronal registers, which are represented by R, U, and X, which is the input. And between them, they exchange information through a dictionary of vectors that is encoded in the plastic synaptic connectivity of phi. As we see, the arrows on the green mean unidirectional plastic connectivity, and the arrows on black mean unidirectional non-plastic connectivity. And now on the right, we have an image of this same architecture, but here we see how the information is being propagated in time through the neural circuit in A, where we have on the top the time and the layer identity. And here we see how we start the information through the input. It flows through the learning coefficient that we see here, and it starts all the information starts being gated by the SimFire gated neurons on the bottom through the whole circuit. And at the end, we achieve a heavy learning update of the dictionary elements. On the results, we implemented this normalization circuit on LCA, which is the locally competitive algorithm. And on the top panel, we demonstrate the normalization of the dictionary vectors of phi. And as expected, we see the decay of the norm of the dictionary values through time. And we see how they decay asymptotically in the first 1,000 time steps. And on the bottom panel, we have the sparse reconstruction of all digits after the convergence of the dictionary. This is just to prove that the LCA algorithm works. And this was done handpicking numbers from 0 to 9 of the NNS dictionary, where the digits were on order with random dictionary values. So in conclusion, we see that our normalization circuit directly normalizes the synaptic weights as a component of LCA. It also prevents instabilities that could generate runaway conditions. And this also serves as a component for other architectures that it can serve as a model that can be incorporated into different neural circuits. And now it's time for questions.